Okay, so now we're going to start an introduction to thermodynamics. I pull up my little sketch pad. Here's my PowerPoint. Now, thermodynamics seems scary, but it really isn't. It's really just you're looking at the transfer of energy. How much energy was involved in a reaction. Thermo, yeah, think of like thermometer or something. And so you think of maybe heat. And so heat is usually, well, it pretty much is always involved in the transfer of energy. And that's the easiest way to really calculate energy, is how much heat is involved. So we're looking at, how much energy in a reaction. Usually looking at heat. See, thermochemistry is the study of the relationship between chemistry and energy, specifically heat. Energy can be transferred through heat. Heat causes two effects. The flow energy caused by a temperature difference, so heat causes a temperature difference. Also work as a result of force acting through a distance. So that would be your physics, It's a force through distance, so through heat you get a temperature change and you also get work done. Okay? So that's all we're looking at. So if you put thermochemistry down, you look at the very basic of it, we're just looking at the amount of energy in a chemical reaction. Okay? There are different types of energy. There's kinetic energy. This is associated with energy in motion, so when you're moving. And so thermochemistry, when we're looking at a chemical reaction, this is the, if you want, the kinetic energy of a reaction. So when we're looking at thermal energy, we're looking at kinetic energy in a chemical reaction. There's potential energy, and that is the energy something potentially could have. So I use this example of a compressed spring, okay? If you compress a spring down, think about how much energy that could be released if you let go of the spring, okay? A lot. So potential energy is converted into kinetic energy. And so chemical energy is what we look at there. And so this is the energy associated with the relative positions of electrons and nuclei in an atom. So basically, we have this chemical. We haven't reacted it yet, but it has the potential to react and transform it into kinetic energy. So it's the energy every chemical has that can be released whenever it has a reaction. Anyway, so there's different energies, basically. There's the energy of when it's actually reacting, which is called thermal energy, and the potential energy we call chemical energy that it could have once it does react. Okay? Law of conservation of energy. So energy cannot be created or destroyed. And we saw this, I think it was chapter 2. We were looking at mass. Well, the same thing with energy. So energy is transferred from one object to another. There's your system. So your system would be, like the beaker. There's a reaction going on in your beaker. We call that the system. And the surrounding is everything else. So energy is transferred from the energy into the system. So let's think about this for a second. Let me draw a fire. Okay, here's my fire. Woo! Okay, that doesn't look like fire at all. But it's a fire. Let me put some logs on there. Okay, I think I'm making it look worse. But here is a fire nonetheless. Let me label this as fire so we know this. Okay, so this is my system. Okay, the fireplace. Okay, system. Because this is what I'm looking at. This isn't a fireplace. The surroundings are everything else. So I'm going to put, here's me out here. I'm enjoying this fire. I'm part of the surroundings, because I'm not part of the system. Okay? But energy from this fire is being transferred to me. Energy, right? Energy in form of heat. Okay? I'm warm now. I was cold, now I'm warm. So that's what we're looking at. We have a system. This is what we're looking at. We're looking at the fire. And that fire, it's transferring heat to everything else, to the room, to me, to everything. And so that's what we're looking at with thermodynamics. So there's a system. So that's what you're analyzing, and your surroundings are everything else. So your system and your surroundings transfer energy back and forth to each other. Okay, so everything's conserved. So all the energy that's released is now put into this room. Okay, all that heat. Okay, so nothing is ever lost. Units of energy. Sorry. So kinetic energy is 1/2 mv squared. M being the mass in kilograms, v being the velocity in meters per second. So if we put this together, we look at the units, we have a kilogram for the mass, and then a meter squared, but that's all squared. So a kilogram meter squared, a second squared, that is a joule. So basically, when you put the units all together from the mass and the velocity, you get a joule. So energy is a lot of times given in joules, or kilojoules, which just, 1,000 joules. Sometimes you see it in calories. We see this, on the back of a food box, a calorie, right? That is actually a unit of energy, and we actually see it in, we call it a big K, or a big C, which is actually kilocalorie. So 1,000 calorie equals 1 calorie. It just to make the number look nicer, because if I say, oh, this has 10 calories in it, you're like, oh, that's not too bad. But if you realize that's actually kilocalorie, so, it's actually like 10,000 calories, it just seems worse, So it's just to make the numbers look prettier. So we're actually looking at kilocalories technically. But anyway, it tells you basically how much energy is released in your body. 1 calorie is 4.184 joules, so there's the conversion there. And then there's a kilowatt per hour. We see this a lot, maybe on your electric bill, you'll see a kilowatt per hour. So a kilowatt per hour is 3.6 times 10 to the 6 joules. So you can convert back and forth to these. In chemistry, a lot of times though, we use joules or kilojoules. In food, we use calorie. And then a lot of times in like energy, like your house or whatever, we'll use kilowatt per hour. But they're all just units of energy. Again, nothing different than saying an inch versus a centimeter. They're all units of distance. It's just a different way of expressing it. So again, the first law of thermodynamics, the total energy of the universe is constant, since energy is not created or destroyed. Okay, so we know energy is not created or destroyed, so all the energy is constant. So all the energy we've ever needed has already been produced. So we're just transferring that energy into something else. Like the heat of the fireplace, is transferring to us to heat the room. Okay, think about melting ice. Okay, we have it. The ice gets energy from the room, heat from the room, if you want, to allow it to melt. Okay, so it grabs energy from the surroundings to melt the system, which is the ice. Okay, now we're going to look at what's called internal energy. And internal energy basically is just total energy of a system. Okay, remember, system is just what we're looking at. Are you looking at a piece of ice? Are you analyzing a chemical reaction in a beaker? Are you looking at the fire in the fireplace? So the system is what we're actually looking at, okay? So it's the sum of the kinetic and potential energy. So it's internal energy, U is what we usually see it as, is total energy. This is a state function. What does state function mean? It means it doesn't matter how you got there. So let me show you this picture here. I think this makes more sense. Okay, so here's our mountain. We're going to climb to the top of the mountain, right? That's the goal. Now, does it matter if I go straight up the mountain or if I go zigzag up the mountain? Do I still get to the top of the mountain? Yes, right? Okay, I still get the same result. Now my pathway is different, but I still start at the bottom and get to the top no matter what. So that's what a state function means. It means it doesn't matter what pathway you use, you're still going to end up in the same result. okay? So you might have taken 5 miles, to get to the top going straight up versus 12 miles zigzagging because it's a little bit easier. But either way, you end up at the same spot. So that's what a state function means. It means it doesn't matter how you got there or how long it took. It's just that you actually got there. Okay, so the delta U, delta just means change in. It's, a Greek symbol meaning change. So how much, if we're looking at the mountain, delta U for path A is 12 miles. It took 12 miles to get there. Versus path B, it took 5 miles. Okay, so delta U is the difference there. So it's your final minus initial. So anytime we look at delta U, that's internal energy, and what we're looking at is what is the total energy in the system. So again, internal energy is always, if a system loses energy, then the energy is gained by the surroundings, okay? So it's just what we said. So if we look at our fireplace, okay? So let's say this is our fireplace, our system, and our system is going to lose energy into the surroundings, okay? So since it lost energy, that's negative sign, and the surroundings gained it, right? Because the room became more hot, okay? Now let's look at the melting ice. Ice is on the table. It's going to grab heat from the surroundings, okay, from the room, and it's going to be put into our ice. So our ice is positive because it gained heat, but our surroundings are negative because it lost the heat. They'll always have opposite signs of each other. Okay, so looking further into delta U, what is delta U? We know it's the total energy, okay? How do we measure that though? Well, the total energy is just heat, which we say is Q, plus work, which is W. So delta U get a different color here. Delta U, okay, this is total energy equals to Q plus W. So this is how we measure it. Q, so let's define everything. Q equals heat. How much heat is gained or lost in the system? Okay, so think about like your fireplace. Okay, how much heat did it lose? Work is just, W is work. Think about, let me think about work. Think about yourself, how much, if you're exercising, you're doing some jumping jacks. It takes work to do that, right? And then at the same time, you're also producing heat and sweating, right? So your total energy your body requires is the work you do plus the heat. Okay, let's look at how we look at the system. Like, if we have to decide if positive or negative. Now this can be a little bit strange, but let's look at this. Okay, so I think the easiest way to remember this, in my head anyways, is that our system is lazy. It's just like us. We do not want to do a lot of work if we don't have to. We would love to just be millionaires and sit around our house and read a book. Well, at least I would. Okay, maybe some of you would still like to work or do something else. But most people, this is me including, I would love to have a lot of money and not have to do anything. Well, our system, our chemical reaction is the same way, okay? So we have heat, okay? Anytime that it gains heat, it gains something, that's positive, right? We want to gain something, in this case heat, we want to become warmer, so that would be a positive sign. Anytime a system loses heat, that's negative, right? Anytime we lose something, we don't want to lose money, right? That's a negative. So we have a negative symbol. Work is the same way. When work is done on the system, that's positive. So it's done on us. Think about a massage. We want a massage done on us. We don't want to do the work. We want the work done on us. and the work done by the system. So whenever you actually have to do the work, that's negative, right? You don't want to do the work. You want somebody else to do the work. And the same thing with delta U. Energy flows into the system, so we get energy that's positive. It flows out as negative, okay? So when you do these reactions, you're going to do some examples, you have to figure out, okay, Q is heat, W is work, but is the sign positive or negative? So that's the hardest part of the equation. I mean, the equation is just Q plus W. That's not hard to do. It's simple mathematics. But the hardest part is figuring out what is the sign of Q and W. Okay, so the next podcast will go into this a little bit more. But let's look at this. An ice cube melts and cools the surrounding beverages. So ice is our system. So don't look at everything else. We're only looking at ice. So ice melts. So does ice need heat to melt? Yes. Okay, right? So it's going to grab heat. So it's going to gain heat to melt. So that's positive. Okay, so Q would be positive here. A metal cylinder is rolled up a ramp. The cylinder is the system, okay? Now think about this. Is the cylinder rolling itself up? No, that's impossible. So somebody else is rolling up the cylinder, okay? So that is positive, okay? So if this said the cylinder is rolling itself up the ramp, then that would be negative. The system doesn't want to do work. But if it's somebody else is rolling it up, that's positive. Steam condenses on skin, causing a burn. Okay, steam condenses. Okay, so we're looking at steam. Steam lets off heat, right? If you have steam and you put your face into it, you're gonna burn yourself, right? So it releases heat. It releases heat. So I'm getting hotter. So that means steam is losing heat, right? Because I'm gaining it, because I'm burned. Okay, so steam is the system. You always have to think about what is the system. Steam is the system. It's letting off heat. So that's negative because it's losing heat. So you should get positive, positive, negative for Q. Let's also look at this here. A system performs 855 joules of work. So it performs work. Do we want to perform work? No, that's bad. We're lazy, okay? So that means work is negative. So let me write this down. Work would be a negative 855 joules. We don't want to do work. And produces 1,422 joules of heat. So it produces heat. So that means it lets off heat, right? That means it releases heat. So that's negative also. So Q, negative 422 joules. Okay? So now that we know the signs, all we have to do is add them together. So 855 plus 1422, 2,277. And that's a negative joules. Okay? Now, if it would have said, work was performed on the system, then that would have been a positive number there. Or if it said it gained 1,422 joules of heat, then that would have been a positive. Okay? So again, the next podcast will go more into it. But now that you have an idea of what thermochemistry is, it's a measure of delta U, which is the total energy, and how we get this energy is Q plus W. So we have to look at the heat involved in the reaction and the work.